In this video we're going to take a look at the ropmev2 challenge on HackTheBox. It's a hard Pwn challenge and the description says "Rop me if you can." So I just solved this challenge yesterday and I was a bit confused. I thought this was a bug with the date, but I realised it's actually 1 year and 8 months and 8 days since the challenge was released, so that's when I solved it. So some of the videos that I've done I said that I solved it like 3 years ago and couldn't remember, when I'd actually probably just solved it like a month ago and couldn't remember, so oh well. So as usual we'll download the files or the file and copy this over to our local directory. And we'll go and do some basic file checks. So we begin by checking the file type, and as usual it's a 64-bit LSB executable. It's dynamically linked, so it'll be using external libraries like Libc to get its functions from. It's stripped in this case, so the debugging symbols aren't available and it'll just make it a little bit harder to analyze. We can check the securities that are enabled, and in this case we have very little protections enabled, so there's no rel row. I think the only other challenge that we didn't have any rel row enabled was Nightmare, where the goal was to overwrite the address in the got table. We have no canaries, so we don't need to worry if there's a buffer overflow, no need to worry about tripping any canaries off. No execute is enabled, which we would expect because the challenge is called ropme, and just like the last challenge we'll be looking to use ROP gadgets from the program rather than injecting shellcode to execute. And there is no pi, so pi is disabled, so every time the program loads in memory it'll have a predictable address. We don't need to work out the base address and then use offsets from there. We'll just be able to hard code in any values that we need, any addresses. We could have a look at the strings to get an idea what's going on in the program. It's going to say please don't hack me. There's a debug string and it's going to print out a pointer to some location. It's going to leak an address for us, and we can see the sections and things that are imported, our libc and the functions that are used. And let's make it executable and run the program, see what it does. So we run the program and it says please don't hack me. We could enter in some characters, we could enter in a lot of characters here and try to overflow the buffer, see if we get a segmentation fault, which we do. There's a segmentation fault there, and if we run it again and just give it a normal string, hello, nothing interesting happens. So we saw the debug string there. We could try and run it again with debug, and we'll see that it's leaked that address, which is the other string that we saw there as well. Do debug again, and each time we do debug this is increasing the value that it's leaking. We could also have a look with ltrace as well. For instance, I tested debug because I saw the string in the program anyway, but if we weren't too sure what to enter there to get some functionality, we could run it with ltrace and see what the string compare does. So here it's reading some data off of us, and if we say let's just give it an incorrect string, you can see there it's comparing the A's that we entered with debug, and it has not printed out the pointer because we didn't give it the right value. We can also see here that it's doing this string length comparison, and the characters we're entering are being changed into N's. So we've put in 4 A's, by the end it's 4 N's here. Let's run it again and put in debug. Put in debug, it compares and it says yep, okay, those two strings match, so it gives us this address. We're going to want to at some point go and have a look, see what this address points to, and then essentially it then resets and does the same thing again. So we could say here hello, and you can see that our string has been. We could take the string here, let's take it to Cyberchef, and we could just put it in here and check for magic. Oh, not that. Not that. Okay, didn't actually find anything from there. We could try that with a longer string. If I go back and do that again and say what is this encoding, we get back this string, so we can go and paste it in there, and yeah, it still doesn't find it. Okay, I thought it would, but well, we can go and try some different encoding types. Here's the ROT13, and that's got us back our response. So the A's that we entered all turned into N's, so it's being they're being rotated by 13 places because there's 26 characters in the alphabet. So we can see exactly what's happening with our input. Let's go and open this up in Ghidra and have a better look at the code and see if we can understand more what's happening. So I'll open Ghidra and create a new project and import the file. I'll speed through the process a little bit here because it takes a bit of time. So because it's stripped, we're not going to have our main function here, but we can either go and have a look through the functions if there's not too many programs. We can have a look for the strings and go and jump to, for example, this debug. We know that's going to be of interest. Okay, that was the actual string there, but we can go and see where it's referenced and jump to the function. We could have also just gone to the entry function, which is right here. Go to the entry function, we'll see this function's called, and this is our main functionality. So we have an int variable that's declared, ivar1, we have local d8, which is a char buffer of 208 bytes. We have this function at the beginning which just sets how the program's going to buffer, we don't need to worry about it. And then we get the printf statement which we've seen, which will say, please don't hack me. It's going to read some 500 bytes off of us into local d8, which is only 208 bytes. There's a clear buffer overflow there. And then it's going to compare. ivar1 is going to equal string compare, so it's going to compare what we enter, make sure it equals debug. If it does, so if ivar1 equals 0, it's going to print out the pointer, which is pointing to the local d8, so it's pointing to the beginning of our char buffer, which we're able to write to here. And then it calls the function. It's actually calling the same function again, so it's recalling this. So it's going to loop back, but it's also going to run this function here, which it's passing in. It passed in our buffer, here, and this is looping through, and this is essentially performing the rot13 that we saw, right? So we have A and M, and that's the 13 positions away. It's doing the same with capitals, and it's basically gonna rot13 our whatever we enter there into that buffer. So because this is leaking the pointer, we have the address of our buffer, the beginning of our buffer, but whatever we enter into the buffer is going to be rotated. So we couldn't just enter necessarily in whatever we enter in there. We might have to deal with rotating first, or might have to find some way to avoid this check altogether, or just bear it in mind. We might need to pre-rotate some of our input beforehand, and we'll also need to be aware of the fact that this function runs again. So it's leaking us this pointer address, but whenever the program runs again, it's going to declare these variables again, which means the address that we've leaked is actually, by the time we get back here, it's not going to be the same address. So we're going to need to basically account for this offset. In fact, why don't we go and let me run the program again, and we'll enter in debug. Okay, so we could take these addresses and then say python2-c print, and then just subtract the address. Should have done this the other way around, but it should be okay. And the difference is 224, so we'll just need to bear this in mind later on. If we are sending more than one payload and we're not bypassing the function restarting, we might be able to control the execution flow, and instead of restarting the function, we could call it to restart to go here instead. But just worth bearing in mind that if we are going back to the start of the function, we'll need to account for that offset as well. So let's go and find the instruction pointer offset as well. How many bytes do we need to write before we overwrite the return address for a buffer overflow? And we'll do that in gdb pwn-debug. So let's just jump straight into creating our cyclic pattern. Create this as 1000 bytes because we know this is 208 bytes, but we're reading 500, so we don't need 1000, but we need more than what we usually use, which is like 100 or 200 or something. So we'll run the program, paste that in. It crashes the program as we would expect it to because we got the segmentation fault earlier. And in the RSP, we want to find out what is the offset. So we've got in here RNNP. You might notice that's looking a little bit weird. Let's do cyclic-L to look up the offset, and we'll see that the offset is 428,527, which definitely isn't right. So obviously we need to take these characters, take them and rotate them. Instead we want to provide this as the offset that we're looking for. And if we provide that, we'll see that we've got 216. So that's about what we would expect to see, considering that the buffer is 208 bytes. And we'll find this anyway in our PwnTools script, as we usually do. So let's go and copy that template over. Just call it exploit.py for now, and we'll open that up. Alright, I'm not going to explain too much about this template because I do it every video and it's starting to increase the time a lot. So if this is the first video you're watching, I'd recommend going back and checking out some of the other Pwn ones before starting on this. So we want to load in a binary here anyway, ropmev2. We want to go ahead and change our find instruction pointer function to use the 64-bit code rather than the 32-bit, and we'll save that. And we're going to need to update this as well, so whenever we run the program it says please don't hack me, so we'll just go and change this to please, did it have an apostrophe? No. Please don't hack me. I'm going to send off the payload. We could have just sent it after me, that'd be fine as well, but we'll set our debugging level, our context level at log level at debug, so we can see a bit more about what's going on. We'll increase our cyclic offset as well, the pattern that we're sending, and take out some of this stuff. I'm going to try and get a shell straight away at the end, so we'll just go to IO interactive, and this is going to be the same here. Essentially we're going to have the please don't hack me whenever we do try to send off a payload. But let's just go and test out our let's test things out first of all and just make sure that the offset is working. I think that's all looking okay. We might want to go and set up a breakpoint for later as well. So it's stripped, so we're not going to have the function names, but we could go and have a look at some area of interest. So for example, we could have a look at the printf whenever this occurs and see what the pointer is pointing to at the time. We could set it to our read call, which is where the buffer overflow is actually going to occur. So I'll set it to the read call for now, 401.1b4. We'll only use that breakpoint if we pass in the GDB argument anyway. So for now, let's just try and run this and see what happens. Okay, and you'll see that we've got the same issue here. It's not found the correct offset. So what I did in this case was add another function, which I'm just going to paste in here with as a basic rot13 encoder. So it'll just return whatever string gets provided as an argument. It'll rot13 in it and it'll return it. We just need to also import codecs here as well. And that means that we can just say whatever cyclic pattern we're searching for here, first you want to rot13 it. Let's see how that goes. And we just have an issue between the conversion between bytes and strings, so we can go here and say we want to decode and now we found our correct offset, which is 216 bytes in. And now we want to grab the leaked address, so whenever we pass in here debug, we get this leaked address back. So let's go and add some code to do this for us. We'll start the program, and then we want to send the debug line, so we'll say send line after, and just grab this please don't hack me, and we're going to send debug in capital letters, and then we're going to receive, I don't know what this is, so we want to receive up until that, so we can print that out, or we'll just do io dot receive until, and I'll grab a copy of this. And then the next thing that we receive is going to be our leaked address. So I'm just going to copy a line that from our previous write-ups, the previous videos, which is going to, it's just going to grab this address and then format it as an actual base 16 address. And we'll want to print that out as well, so we can just say info, the leaked address is %#x, and then pass it the leaked address. And if we run that now, we'll see that it's run through, we've found our offset, and we have leaked our address, and it seems to have extracted that quite well. So next what we want to do is just we could just go and verify in GDB and make sure we know exactly what's happening whenever this loops through by sending some additional input. So I'm going to grab a copy of this and I'm going to send it a cyclic pattern of 216. That's our overflow is at 224 for the return address. We don't actually want to overflow the buffer, just want to send this off and see what happens, because we know if we send this off, it's going to, first we're doing the debug, we're leaking the address, we grab the leaked address, and then it's going to call the function again. So we want to go and have a look and see what happens when we look 224 bytes back to our offset. If we remember, each time we printed out this address, it was 224 bytes forward. So we'll just go and test that out in the debugger and see what's happening. So we have a breakpoint set up at the read call already, I think. So we'll just put in GDB here. You can see it's set up the breakpoint for us. Let's continue because we've not got the leaked address yet. Okay. It closed there. Let's try and set that IO interactive back. And you'll see this time we leaked our address, but it didn't actually, the program didn't end because we went into the interactive mode. So let's go and have a look now. We've got this address, this leaked address. We'll do x and then the address. Let's do x over s and the address. And it has the debug in it at the moment. What if we do x over s? I'll do x over 50s. And we'll do the address minus 224. Okay, not seeing our string there. What if we, let's continue again. We've got an invalid address. Okay, so now we've continued, so it needed to loop through again and actually take that input, but now you'll see at minus 224, if we, in fact, we don't need the x over 50s. Oops, yeah, no, that's right, x over s. So this is a string that we have in there. So if we were to take this and go to our rot13 and paste that in, you'll see this is actually the beginning. So this is the 216 bytes that we've sent. So we know after that loops round, the address that we have there, if we subtract 224 from it, we're going to get to the start of our buffer that we've entered. But whatever buffer we have entered is going to be rotated by 13 spaces. So we'll either need to bypass this, we'll need to reverse it, or we'll need to rotate our strings before we actually send them. So just wanted to go and verify that and demonstrate how to check to make sure that the offsets are as you would expect and that you know what's happening to the input. Okay, so let's talk about the exploit plan here. I'll let you know in advance that what I'm going through, first of all here, the payloads that will build up only work locally. So in order to get things working remotely, I had to completely change my attack plan. So if you're short on time, you might want to skip down at the chapter section. You can skip to look at ROP gadgets again or something like that, and that will be us building the remote payload. If you do want to see where I went wrong here, I mean at the end of the day it did work locally, but keep an eye out and you might notice, I'll mention it later, but you might notice one glaring issue in my approach which didn't really make sense in terms of being the intended solution. But anyway, my initial plan was this. So kind of similar to the last ropmev challenge, I figured we could do a return to libc attack here. So because we have our overflow here, we could send some ROP gadgets to print out the address in a global offset table of a function. In my case, I'm going to choose the read function, but you could choose something else. Essentially, we'll overflow the buffer. Right here. We'll overflow the buffer here, and we'll call printf again because we have the address of printf right here, and we'll pass into printf as an argument the address of the read function in the global offset table which we want to leak. And then once we have that, rather than continuing with the program and running down to this rot13 function, we can just redirect the program execution to the start of this function again. So we'll do printf, we'll do our buffer overflow here and leak the address, and then we'll return right back to line 9 to do the printf again. And that way the rot13 isn't happening and these variables don't get redeclared again, so we don't need to worry about any offsets and things there. And then from that point, because we've got back to printf, the read is going to be called again, and we're going to get another chance to send a payload. Again, we wouldn't need to worry about it being rot13 because that code's never actually going to be reached. And then we'll just call the system function from libc with the bin sh string, similar to the ropmev1 challenge that we did. So you might notice an issue, not an issue necessarily, but kind of a hint that that's not the intended solution. If not, I'll point that out after we get this working locally. So let's go back to our script and let's start building up this payload. We don't need to send this off, we're just going to send off a payload after this. And let me just format this a little better. So at the offset, which is 216 bytes, we're going to send this list. And the first thing we're going to want in our list is a pop RDI gadget, which we've not found yet. I'll find that in a second. The next thing we're going to want to do is we're going to want to pop an address from the got here. So any of these functions which are going to be called, it's essentially going to look to libc to find out what these addresses are, and it's going to populate the got table. So in my case, I chose the read function, so we can say elf.got.read, or we can pass that in as a dictionary as well, whichever syntax you prefer. And we're going to pop that into the RDI, and then we're going to call elf.plt.printf, and that's going to print the address of this read function. And then where do we want to return to? So let's go back to the code. We have our printf right here, which is 401.196. So we could go back to that. We could also just go straight to the read as well. Let's grab this address. And that'll be where we want it to return to. So we need to get the ROP gadget there as well. I'll just do that with ropper. So we'll do ropper -- file ropmev2, and then we'll search for pop RDI. Take a copy of that address, paste that in, and that should be everything we need. So we're going to send that off just like we did up here, but we'll be sending the payload. Oh, actually, I'll just uncomment this. And then we're going to want to receive io.receive, and then it's going to leak us the address. So I'm just going to grab from our last example the code to unpack the address. So we'll say here got read is equal to, this is just from one of the last scripts. I just use the same, just copy and paste this for each time we're leaking addresses. And then we can print this out as well, so we'll say info got read is %#x and pass in the got read. So if we run that again now, we put in printf here, just typo, run it again, we get an end of file, so it's leaking the address. Let's go and change this. Let me see if I take this. Let's print out what it's receiving here. Print io.receive. That's just a new line. Okay, so we'll receive the new line, and then what does it receive? Okay, it's not receiving at all. Let me go back, and rather than jump into our printf, I'll just jump back to the start of the function and see what happens. 116b instead. Let's try that. Okay, so now we have our address. Okay, so we'll take out one of these print IO receives, and now we're getting our got read address. So let's go back and run that with GDB. Okay, we'll continue until we get our got read address, copy that, and then just go and make sure here that that equals the libc read, which indeed it does. So from here we can find out what's system, and now we can get our system address. We could calculate our offset here as well, I believe, if we do x, and then just minus the system address, and it gives us the result A6030. Presumably, if we do that as an int, 679987, but typically we'll go and do that with readelf anyway. So let's go and calculate our offsets here. Let's first of all get the libc, and then we can copy that. We can copy that file location, and then do readelf -s and grep the read function, and we'll see here it's this one here, the EEE80. So we can just go and subtract this to find our libc base. Is equal to our leaked address. Oh, I'm at the wrong place. It's equal to our got read minus EEE8. Was it 08? 80. Okay, and then we can just go and calculate our other offsets from there as well. So we'll do the same now with system. We can grab our system offset and say system is equal to libc address plus 0x, paste that in, and then finally we'll look for our bin sh. So we can do strings dash a dash tx, and okay, we still need the address of our libc. So we're going to grep bin sh, and instead of readelf, we're going to use strings dash a dash tx, which is just to represent it as hex, to interpret it as hex. So our bin sh is equal to libc plus 0x. Now notice these addresses are the same each time for me, so I'm just always showing how to do this in a video, but really, you know, these addresses don't change for me because my libc versions remain in the same. But obviously whenever we go to do this remotely, we'd need to find out what the got read address is there, and then we'd use that address to try and work out what version of libc it is. There might be a few different possibilities, so then we would go through and test each one and see which one works for us. But there's our addresses. Let's put those together. In fact, let's also print these out. So we've got a libc base, we've got a system, we've got a bin sh, and we'll just finally go and test this out, run it with GDB, hit continue past the breakpoints, and here we've leaked our addresses. So let's take the system one, make sure it's correct, do x and paste that in, and yep, it's libc system. and then our bin sh string, we'll do x over s to print it as a string, and we'll see, yeah, that's bin sh. We could have just found it in here as well, so we could have just done search -s for a string, and then look for bin sh, and that would have also found us the address, and then we just need to calculate the offset from there. So all our addresses are okay. Let's go and put together our return to libc payload to get the system bin sh executed. So let's put together our second payload. I'll just grab a copy of the first one. And again, we're going to be using a pop RDI gadget, but this time we're going to pop in our bin sh address, and then we're going to call system. We just want to send that off, so we'll do io.sendLine payload, and then go to interactive. Let's test it out. And you'll see here we've got switch to interactive mode, run some commands, and we'll see that we have indeed got a shell. So locally this was a success. We returned to libc, we've got everything executed, and typically now then we would go and have a look at executing this on the server. So let's actually go ahead and try that. So we can just grab a copy of the address and port number, and using the template we're able to just pass in remote in capital letters and then the address and port separated by space. And you'll see that switch to interactive mode, but this time we got end of file, which we would expect because they're not likely to have the same libc version as us. So what we'd normally do is just grab the got read address that we've leaked, and we can go and take that to the libc database. And what we would typically do here is look for the read. It shouldn't actually matter, we should just be able to just put in read, but I'm just to make sure, we search for that and we get nothing was found. Right, so if we were doing this locally, let me do that locally again. We leak our addresses, we grab this got read address, and if I just paste in, if I just have here read and put that address and go to find, it's going to find a potential libc versions for my system. Could be one of these three, and then we would just go and look at these offsets and see, okay, these are the offsets we need to use. In this case, this is my libc version, and you can see then the bin sh offset, the system offset are the same as we have in our code. So the problem is here is the same as the last challenge, the ropmev challenge that we went through. We weren't able to identify the libc version, and looking at the forum for the last challenge, I found that the libc version is from 2002, I believe, and it isn't actually available on here. So it was like the Ubuntu 9 2.23 or something, and if you go and have a look at all the libraries in here, it isn't actually present. So I tried actually downloading the source code on the last challenge and trying to identify the offsets that way, and just never actually got it working. So my thinking for this challenge was, because although we have the addresses from the last in our code from ropmev1, we have the offset to system and we have the offset to bin sh. We don't know what the offset is from read to the libc base. So I first tried to see if we could leak puts like we did in the last challenge, but we don't have puts being called here. I then tried to just solve ropmev1 again, log into the server, and then use readelf to go and identify the offsets there. But readelf and strings and basically everything is not installed on the system. So none of those was successful. So once again at this point I turned to the forum hints and found that actually we're not, even if we do manage to identify the correct version of libc, we would still have problems because that's not the intended solution to the problem. So I went back to take a look at the ROP gadgets, but I'll just mention as well, what I should have really noticed when going through this is we leaked this address at the beginning and we never actually used it. So the fact that the program leaks us the address and we didn't end up using it at all is kind of a sign that probably it's not the right method to solve it. So bearing that in mind, let's go and find the actual solution. So let's go back to Ropper, pass in the file, And one of the gadgets we see at the bottom here is the syscall gadget. So this is something that we'll be able to use. Let's go and take a look at the system call table for Linux. So here, to find the implementation of system call, grep the kernel tree for OK. So here we have the format for the system calls. So there are different modes depending what we provide in the RAX register will depend what system function is going to be executed, and then it tells us what the order of the parameters will be and what kind of data they're expecting. So in this case we can have a look for execve, which is the code 59, and here we can pass in essentially to our RDI. We're going to want to pass in the first parameter here is the RDI, and we're going to want to pass in then our bin sh to get a shell. So 59 in the RAX and bin sh in the RDI, and we may also need to be careful about the RSI and the RDX, because if these have values in them which will be interpreted, let's go down to the execve again. So these would be used as environment pointers, I guess, or as arguments. So we'd need to be careful that it's not sending in something which is going to interfere with the program there as well. So let's go and grab some of these addresses. Here's our syscall address. So we'll go and add this as a gadget. Put that at the top. Syscall is equal to 0x. We also then need our pop RAX as well, which we need to put 59 into the RAX to equal the execve call. And we could just look for that, but I'll do the search here as well. Search pop RAX, and there we go. 1162 0x. Okay, so and we may also need to do the RDI, the RSI, and RDX as well. But that'll do for now. So we're going to take out a lot of this code. We're not going to bother leaking any new addresses there, or any of our got addresses. We don't need to do that. So we'll take this out. Take this out as well, and we're just going to build up our payload slightly differently here. So we need our bin sh string. So let's just set this up as bin sh. Put a null byte at the end. And rather than just going straight to our offset now, we're going to want to insert this at the beginning of our offset. So I'm going to say here that our padding is equal to, and you could just send in some junk. I'm going to send in no operation instructions just to make sure doesn't cause any problems elsewhere. And we'll say that we want to subtract the length of bin sh essentially from that. So we'll say times offset minus the length of bin sh, and that'll be our padding. So instead of sending in the offset here, in fact we'll take out this dictionary altogether. We're just going to do this as a list, and first thing we'll give is the bin sh string and then our padding. So that's going to equal up to the 216 bytes, and then we're going to say pop RDI. And what do we want to pop into the RDI? We want to pop the bin sh string, and the bin sh string is at the address that was leaked to us minus the 224. If you remember, we whenever we tested earlier, we kept leaking the address, and then we went and subtracted it, and we found it was minus 224. So right here we'll just say leaked address is minus 224, and now the address of the bin sh string is now popped into the RDI. So we want to go ahead and prepare the system call as well. So the first thing we need to do there is tell it that we want to do the exec. So we're going to do pop RAX, and into the RAX we want to pop 59. That was the execve. 59 is the number that we want in the RAX, so we'll pop that in, and then we may need to zero out the other registers as well. Let's just test this out first of all. If we do syscall, and then we'll send that off and see what happens. So So we've got an end of file there. Let's try and debug it. What I'm going to do is I'm going to go move this breakpoint to our system call. So whenever we have this syscall, that's exactly where we're going to want to analyze what's in the registers. So let's set the breakpoint there instead, and we'll do Python exploit GDB. We'll run that. We'll stop at our breakpoint. I can never snap these windows, which is kind of frustrating. And then I'm just going to go next to the next instruction, and right here we'll see what we have in our registers. So you can see here at the moment in our RDX, RDI and RSI we have it's all pointing to our OVA/FU here. So if we take that to our ROP, we'll see that that's actually the bin sh string. So we need to bear that in mind. So let's close that down. Let's close that as well. And before we pass bin sh, let's pass it to our rot13 function, and then we'll add it to the payload. Try and run that again. Alright, so we can do Control and C. We can see the next thing here is a syscall. It's going to execute the execve, and it has in it as the path is bin sh, as the argv is bin sh, and as the environment is bin sh. So that's potentially going to be an issue for us, but at least it has the bin sh in now. Let's continue, and we get our invalid address. So yeah, that is an issue. Let's go and clear out those other registers so that they're not causing any problems. So it's the RSI and the RDX we want to zero out here. So let's do ropper -- file ropme, and we'll -- search pop RSI. So we've got pop RSI there. It comes with an R15, and pop RDX, which comes with a pop R13 as well. So we'll just need to put in some junk to fill those in as well. RSI R15, pop RSI R15 equals 0x, and then the same here, pop RDX and R13 is equal to this address right here. So we just need to prepare those as well. So pop RSI R15 first of all, and if we put in a zero this out here, that's going to deal with the RSI, but we also need to deal with the R15 as well, right? So we don't want to pop this into the R15, we want to pop 0x0 into the R15, and then we just want to do the exact same thing with our pop RDX as well. So just copy that, paste that in, and let's test this out. It runs, we get switch into interactive mode, ls is working, id is working, so that's looking good. Let's test it out on the remote server. So I'm just going to grab that address again, and we'll run remote, and you'll see here we get lol nope. So it has connected, switched to interactive. We didn't get our end of file, but we got lol nope. And if we try to run commands, we're not going to get anything. So I'll confess that I actually, when I was looking for the hint, or when I was looking to find out what to do about not being able to find the correct libc library, I noticed some people discussing the fact that you can't connect with a bin sh shell. So we're just going to change this from bin sh to bash. Call that bash sh. Let's paste that in there, and let's just change this to bin bash. And if we try to run that again, switch into interactive mode, and you'll see that we've logged in and we have our flag there. We're logged in as root. So that's the challenge solved. What I'll do as usual is try to make this script a little bit more automated and make use of the functionality in PwnTools to search for gadgets and to use ROP objects as well to kind of provide some automation. Okay, so you can see the code side by side here. I'll put both these scripts up on GitHub. This is our original code on the right, where we defined all of our ROP gadgets manually, and we built up our payload. In this case, we're creating a ROP object, so that's this ropmev2, that's this exe that we're loading in, the elf, and that means that we can go here and we can say print out all of the gadgets. So let me just quickly go in Python autorop, and if we do that, it'll actually print out all these gadgets for us. So rather than manually entering those like we did on the right, we could actually just search for them using the ROP object. In this case, it's even better because we don't actually need to look at the ROP gadgets at all. We create this ROP object, and you can see here this call argument which says resolvable. As long as this can be looked up via resolve, then we'll be able to call it. So in this case, we're calling execve, and we don't need to even say that it's code 59. We don't need to worry about zeroing out the RSI and the RDX because it'll essentially build all of that up for us. All we need to say is what command do we want to call, which is the execve, and what do we want to pass as a parameter. Now we can't just pass bin sh or bin bash here because it needs to be rotated, and we need to pass because we need to pass the address. So in that case, we write the address just like we did last time, and we're passing the address in as the argument. So you can see all of that here, and it just means we don't need to worry about popping the RDI, popping the RAX, popping the RSI, popping the RDX. Did I say two of the same there? Anyway, yeah, video's getting too long. So that's going to do all that for us. If we wanted to see how it's doing it, we could say here pprint, and then we'll do rop.dump, and if we run it again, it'll actually come back and show us how it's built that up. So it's actually, the ROP chain that it's created is a lot larger than what we put together on the right, but you can essentially see what it's doing here anyway. We have our pop RAX, you can see what it's popping into the RAX, and we have our syscall, we have the parameters that are being prepared. I'm actually surprised, I thought it was going to look a little bit more like what we have done here, but yeah, that's basically doing all that for us. And just to confirm then, if we run that, well, I was already running, but yeah, if we run that, we've got interactive mode, there's no ender file, so we can list, we can check our ID and things like that. We can run that remotely as well. Let's go back to our remote and change this to autorop. Run it on remote, and we also get access, we're logged in as root, and we can print out the flag. And that's been the ropmev2 challenge. Hope you've enjoyed this video. It's the last hard challenge in the retired Pwn series so far, so there's only one challenge left, which is the Dream Diary, I think it's called, which is rated as insane. So hopefully I'll get time to do that at some point soon as well. And hope you've enjoyed the video. Any questions, comments, leave them down below. Thanks.